Okay, can you guys hear me out there? Okay, sorry for the deleting the Canvas link there. It was a mistake on my part, but it's been obviously re-uploaded because you're in the chat session now. So what we'll do is get right into the continuation of our discussion on nomenclature. So we have a couple more functional groups we're going to go through. It's like ketones, acids, esters, amides, and acid chlorides. I'll show you some prompts that you can work on to help you practice these skills, and I'll take any questions, and then we'll transition into conformational analysis. So conformational analysis is pretty important because it applies to figuring out how reactions can occur through major and minor pathways to give different products. So let's go ahead and get started. I think we should all see the slide deck here. So we have a structure that's shown. I'm circling it with my mouse. And so we're continuing the activity of figuring out the name of the compound. So maybe what you can do is consider the major functional groups present in that molecule, sort of identify what they are, and we can use that information then to figure out what the parent is, and then from our sort of first step nomenclature, after we count the longest chain, we can then modify that name to the major functional group, giving it the parent suffix. So maybe first things first, how long is the longest carbon chain? So 7 carbons, that might be not dark enough as I'm taking a look. So let me grab a couple other different markers here. So Ian basically answered my next question. So if we're at a 7 carbon chain, and again, we want to know C1 through C10 so we can figure out what the carbon sort of chain is. So this is a heptane derivative. What functional groups are present then in this molecule? So we have a ketone. What else do we have? Alcohol. So the other sort of thing off the main chain is a methyl. So those are the 3 things that are off the main chain. Now, basically, what we have to determine is of the functional group present, which one takes priority in terms of altering this name to indicate like what the major functional group is. So Taka is fast on the draw here and says it's a ketone. So that's correct. And again, the reason we do that, let me sort of scroll back up on the slide deck to show you the functional group priorities. So I'm circling that box now, functional group priorities. And so the priority really is based on what I like to consider the oxidation state. So if you look at the ketone, that carbon has 1, 2. So I'm just counting 1, 2 bonds. This alcohol only has 1 bond to a heteroatom. So since 2 is greater than 1, that gets the priority in altering this name. So for a ketone, we drop the ending E and we add ONE. So that's, I'm highlighting that sort of with the mouse now. That's the functional group priority. The ketone is 7. The suffix changed to ONE, so this is heptanone. So the thing with a ketone is the carbonyl is always internal to the carbon chain. So you have to identify with a number out front here where this occurs. So what number should I write here that tells us where the ketone carbonyl occurs? So it occurs at 2. And just let me be clear that the 2 that I already wrote there is not this 2. That 2 is just counting these 2 bonds to determine priority. So maybe in the green marker, I can write the numbering system. So if we start here, 1, 2, 3, 4, 5, 6, 7. So that's why I like these colored markers, because we're using them for different purposes in terms of the numbering scheme. So I numbered the chain that way, as we can recall, to give the major parent the lowest number, 1, 2. If we numbered it the other way, 1, 2, 3, 4, 5, 6, the ketone would be at 6. And typically, you know, the rules say that you need to give the lowest numbers to everything. So you really want to give the major functional group the lowest number, and that will sort of assume that everything else also has the lowest number. So then we have 2-heptanone, and so why don't we just sort of go back to the problem? You can put in your response. What do you think the correct answer is then, looking back at the slide? So 4-hydroxy 5-methyl 2-heptanone. So again, to explain that, the ketone is the parent, so that functionality is incorporated here. The methyl and alcohol, the alcohol is named as a hydroxy substituent. So again, hydroxy, H occurs before M, so that's why you get this order. H before M, 4-hydroxy 5-methyl 2-heptanone. So if you look at choice D, 4-hydroxy 3-methyl 6-heptanone, the reason that is not correct is because when you sum these numbers, 4 plus 3 is 7, plus 6 is 13, versus 4 plus 5 is 9, plus 2 is 11. So the sum of those numbers is less than the sum of these. So this tells you, based on the rules, that A is the correct answer. So ketone priority has nothing to do with order, but more to do with its effect on heptane. So Tenley's question is asking about, the ketone priority. Again, when you look at the stuff that's bonded to the, so here's the longest carbon chain I'm highlighting with my mouse. You have that carbonyl, the hydroxyl, and the methyl. You alter the chain name according to what functional group takes priority. And the way you figure that out is typically the highest oxidation state. So again, let me just sort of go over what I mean by that and how you do it. So my teaching philosophy, which I can share with you, is I really like to approach organic chemistry from an oxidation state analysis. So let me circle the longest chain so we're all on board with that. So there it is. That's how we got the 7 carbon count. Now, if you look at the stuff sticking out of the circle of trust here, you have the carbonyl, the hydroxy, and the methyl. The oxidation state, what I mean by that, this carbon's bearing, let me use the blue here. This carbon is bearing a carbonyl. All I'm doing is counting 1, 2. That's where that number comes from. This carbon has the hydroxy. It's just a single bond. It's 1. This carbon's bearing a methyl group, carbon. So I would say its oxidation state is 0 because there's no heteroatoms. So the priority 2 is greater than 1 is greater than 0. So by 2, I mean that group, that ketone. So that tells you what the main functionality is. And yes, that is how you alter this original heptane to get to the heptanone. So you will always do that for every sort of molecule you encounter. You have to figure out the longest chain and then what is the parent functional group. Any further questions on the ketone? So seeing nothing in the chat, let's move on to carboxylic acid. So looking at this molecule now, what's the longest chain? So C6, what is the alkane name for 6 carbons? So that's hexane. So notice I just circled that. See this group here? What group is that? So yeah, Mac, let's use the full term there. So carboxylic acid. And just like in aldehyde, a carboxylic acid always has to be at the terminal carbon. So as such, it always has the highest priority. So let me go back to the slide. See now, carboxylic acid is the #1 priority functional group. It doesn't matter what these other substituents are, this takes priority. So we drop the E and we change it to, so we drop the E, we add OIC, then space, then acid. So hexanoic acid. You do not have to put a 1 in front of that because it's implicit that an acid is always the number 1 carbon. So based on that information, let me go back to the problem. What do you think the correct name is for this compound? So I see B as in boy is the most common response, so that is correct. So the NH2 is an amino group. The F is fluoro. So we have 1, 2, 3, 4 amino, 2 fluorohexanoic acid. Again, let me just reiterate. The substituents are listed in alphabetical order. A is greater than F. Notice how 4 and 2, those numbers are just associated with the alphabetic order of the substituent. So don't be fooled by choice A, where 2 is the lower number, 2 fluoro, 4 amino hexanoic acid. This is wrong because the nomenclature rules state you have to list the substituents in alphabetical order. So are we good with acids? So the next one we're going to look at is a carboxylic acid derivative. So it's this compound here. I'm calling it an acid derivative because you have an oxidation state 3, which I'm showing with my mouse. We have 1, 2, 3. 3 bonds to a heteroatom. Now this is no longer H, it's carbon, so it's an ester. So let me show you on the document camera here 2 things that are pertinent to answering this question. So here's the structure. This is an ester. An ester has 2 components. So I'm gonna draw sort of a dashed line here. And to the left, I want to call that the alcohol component. And then to the right, I'm going to call it acyl, ACYL component. That's just based on how these structures are made from their responsible starting materials. So the way you name these, the alcohol portion is named first, and then the acyl portion. So let's do 2 things. Count the maximum number of carbons in the alcohol and change that to the substituent alkyl, and then find the longest carbon chain in the acyl portion, and then figure out what the substituents on that are. So if you look at the format of the answer choices, there's alcohol portion, then a space, then the rest of the acyl fragment. So how many carbons do you see here on the alcohol portion? So there's 1, 2. So C2 is ethane. So this is named as a derivative, so ethyl. Ethyl and then space. And then what's the longest carbon chain over here? Yeah, I think it's just 5. So what is the C5? What's the okay, so Taka says pentane. So pentane is what we're going to basically change. We're going to drop that E. So let me circle the 5. Now note what I'm going to do now in terms of the numbering. Oh, I see what you guys are doing now where you came up with 6. So you're counting 1, 2, 3, 4, 5, 6, right? So you're counting down this way. Okay, so the reason you can't do that for an ester is because this carbon, which I just highlighted in green, again, that's at oxidation 1, 2, 3, oxidation state 3 here. That has to be included in the main chain because that's how we alter this E to indicate it's an ester. So we're going to number this 1, 2, 3, 4, 5. So I understand sort of how you got 6 now. Initially, I wasn't seeing it. So just like with an acid, the carbonyl group bearing the oxygen has to be included in the main chain, and it's typically carbon 1. So now that we've done that, it's 5 carbons. We drop the E, then we add OATE. So this becomes pentanoate. We do not specify the location of the OATE because it's assumed it's always position 1. So then if we look at these substituents, at the 2 position, we have 2 ethyl, then 3 methyl. So we're going to put all this together. So based on that, what do you think the correct answer is based on your based on the choices? So ethyl, 2 ethyl, 3 methyl pentanoate. So this is 3 methyl. So 1, 2, 3. The methyl group is outside, so it's a substituent. So the correct answer is C. So let me point out where these things are. We've named first 1, 2 carbons. ethane, it's a substituent, so it's ethyl. Then we figured out the longest carbon chain here that has this oxidation state in it. So 1, 2, 3, 4, 5 pentane. We changed the E to OATE, so pentanoate. Then we have 2 ethyl, 3 methyl. So whenever you see a substituent followed by a space and then this ending, that's telling you it's an ester. Questions on the ester nomenclature? So the next two are also carboxylic acid derivatives, meaning they have an oxidation state 3. So the next one is an amide. So as you can see, I'm highlighting with my mouse. There's the amide portion. This is at oxidation state 3 because 1, 2, 3, that means that carbon has to be position 1 in the longest chain. Now the difference between the ester and the amide, this has 2 substituents on it. See 1, 2, and you have to name them separately. So without me going over it on the document camera, why don't you look at the potential answer choices and see which one makes the most sense to you based on everything you've seen so far. So yeah, I think, you know, A is definitely the correct answer, and the fact that you arrived at that indicates to me that you have a firm understanding of the logic of the rules of nomenclature. So we're naming the groups bonded to the nitrogen first. The NN, that is indicating those groups are bonded to the nitrogen. They're both methyl. That means there's 2 of them. That's where we get the dimethyl. So see NN dimethyl. There's a space. The longest carbon chain is 1, 2, 3, 4, 5. So pentane. We drop the E and we add amide. So I mean that tells you right there it's an amide functional group. So from where we count 1, 2 bromo, 3 hydroxy. So B is greater than H, so that's how we get A is the correct choice. So choices B, C, and D all have so Tenley, the space indicates it's an amide, not an ester. The reason the space is there, which you don't see the space in other nomenclatures, is the fact that you're sort of naming 2 different parts of a molecule. So you have this sort of amine part, and then again, this is an acyl part. So that's why the space is there. Choices B, C, and D all have a fatal flaw in them in the sense that they're shortening the longest chain and then adding an extra group or groups as substituents. So let's understand why, say, choice B is wrong. The NN dimethyl, that's correct. 2-bromo-3-hydroxy, that's correct. But now look, this name is calling this methyl group here as a substituent of a 4-carbon chain. So 4-methylbutanamide is incorrect because it's not considering the longest possible chain. And so I think you can see the logic in these rules is that when you start doing things like in choice B makes the name unnecessarily longer and more complicated. The same thing with C. It's saying, okay, here's the 2-bromo. Now see this 2 right here, this second 2. It's saying that this entire group, 1,1-hydroxypropyl, everything within this parentheses is bonded to the 2 position. And the longest chain is 1,2. So you can see that we're building complexity into this name that is not needed. So 3 just reverses the location of the D reverses the location of the substituents, and that's incorrect. You also have this 4-methylbutanamide, which is incorrect. So hopefully you get an appreciation of the rules that you're generating a name that has the simplest carbon chain with substituents. So now the last one is another acid derivative. The tricky thing here is that the acid chloride has an oxidation state of 1, 2, 3, but so does this nitrile or cyano group. So that carbon is triply bonded to the nitrogen, so triple bond 1, 2, 3. So what takes priority between this and this? We go back to our slide here on priorities. We scroll down, we see acid chloride is greater than nitrile, or it's alternatively called cyano, right? Because this has greater priority, that alters the parent name. So this is going to be named as an acid chloride. So given that information, what do you think the correct answer for this one is? So we have a couple straight responses of D as in dog in the chat. So D is the correct answer. Again, oxidation state 3, it's at the terminal. It has to be included in the longest carbon chain. So we have 1, 2, 3, 4, 5, 6. That's hexane. We drop the E, we add OYL, hexanoyl space chloride. So this one's a little different than the ester and the amide in that this portion is named last. So everything bonded to that is then a substituent. So you have cyanomethoxymethyl. 2-cyano, 3-methoxy, 4-methyl hexanoyl chloride. So Taka's asking about this dotted line here, that the acid chloride is not named as a substituent. So if you have a compound that has 2 basically, let me draw out this is sort of what Taka's referring to. You have an acid which takes priority, and then you have an acid chloride at the other end. I think, yeah, that's definitely that's definitely a head scratcher. I'm not sure I know the formal rules for doing that. It would definitely be named as a carboxylic acid. What this whole thing as its own substituent, I'm not terribly certain. A carbonyl group by itself is referred to as carbo. So I'm not sure what that would be. I wouldn't let that sort of tank your understanding of this material when you get into, I would say this is more of a special case in a sense. So I'm sort of dodging the question here because I don't know the right answer. I can look it up and get back to you. I'm not terribly certain. So let me look this up. So when things get super complicated, there's computer software that actually does this naming, but I think we have a good grasp on the basics. Before we move on, let me ask you, what do you think is wrong with A in C? And that sort of gets to what Taka had asked in her question, and Aiden had looked up on ChemSpider, 4-chloro, 4-oxo-butanoic acid. So they're calling the carbonyl group oxo. So 1, 2, 3, 4. So butanoic acid, we understand that. The 4 position has a chloro, and they're naming this as oxo. So 4-chloro, 4-oxo-butanoic acid. I'll buy that. Seems reasonable to me. So A and C sort of also get to what Taka had asked, in that if you examine these, they're not including the carbonyl functionality as part of the name. So that's sort of a subtle distractor and why those are incorrect. So maybe let's spend a couple minutes on some following activities. I'll post these slides in Canvas, but what you consider, you can sort of think about now. We won't go through it all because it will take a little bit of time. Just as an exercise, if you're given the molecular formula C5H8 and on a separate sort of consideration C5H7 ClO2, if you're given those molecular formulas, look at the prompts for the skills demonstration. Draw all the possible constitutional isomers for each. Then name each of those according to the rules we just went over. What functional groups does each have? Then of the main functional groups, where would you see those in the infrared spectra? How many unique carbons and hydrogens does each have? So where would they occur in the carbon and proton NMR? And then finally, of each isomer, what is the most acidic hydrogen in each? So I like these really open-ended activities because then it gets you thinking in making connections. So let's just sort of kick off. Maybe let's kick off this one, this second one, just briefly to get everyone started. C5H7ClO2. How many degrees of unsaturation are present in this molecule? So remember, chlorine adds to your hydrogen count. Oxygen does nothing, so we're looking at C5H8. For N equals 5, we should have a maximum of C5H12 hydrogens. So we get H4. The degree of unsaturation is H2, so that gets us 2 degrees of unsaturation, as we see in the chat. Now, how would you sort of go about doing this? Because there's going to be a Schlode, and that's a unit of measure, Schlode, of constitutional isomers. 2 degrees of unsaturation. I would say a way to approach this in a logical fashion, start with your C5s. Then you can have, let me ask you a question before I just write it. Of 2 degrees of unsaturation, what are the possibilities for what those things could be? What are the scenarios? So let me take Taka's response. 2 pi bonds. So that's one scenario. What's another scenario? So double bond, 2 double bonds. Sort of running out of space here. So yeah, look at the scenarios that 2 degrees of unsaturation can be. So with C5, what I mean by that is a linear chain. Under here, how can you put 2 pi bonds? There'll be multiple ways you can do that. Aiden says diene, alkyne. Under here, 1 ring, 1 pi bond. Yeah, that would be a cycloalkene. Under here, 2 rings. So each of these scenarios is going to have multiple structures, right? Then you can knock it down to C4, C3. I don't think there will be any at C2, so just because you'll be doing some redundant things. But what you can do in terms of practice of everything you've learned so far, the putting it all together, building it up, use this as guidance to propose structures under each of these categories. Then just go ahead and name them. Figure out what the main functional groups are, recall your IR data, your NMR data, and your pKa data. So that's a good way of synthesizing all of this stuff from a very simple prompt. So what I'll do is I'll post these 2 different slides in Canvas as a discussion. And as you think of things, just go ahead and post them in Canvas so your peers see your thought process. I think a lot of students probably learn better if one of their peers explains it to them in a more conversational tone. I encourage you to be engaged in that regard. So any questions on nomenclature before we switch gears a little bit? So a part of chapter 4 is studying alkanes, which is nomenclature. We've done a little bit above and beyond because we've looked at all the other functional groups, which I believe is important in understanding the rules in general, or looking at all the functional groups. But another part of chapter 4 is conformational analysis. And so what do I mean by that? Let me just put this molecule down on the document camera. So this is, we have 2 carbons, each has 3 and 3 hydrogens. So this is ethane. So let me just do, that's good. So conformational analysis is the consideration of what I want to call steric interactions within a molecule. And maybe this will make a little bit more sense if I draw something first. So even though we're going to look at this molecule, let me draw this first. So here's butane, right? 1, 2, 3, 4 carbons. But this is also butane. You would hopefully agree with that statement. Sometimes students get confused because these are static lines, right, that are indicating a structure. This is drawn one way, this is drawn another. So students sometimes get confused and say these are not the same molecule. They are the same because the carbon count, the hydrogen count's the same, but they are different in the sense that they are called conformers. So what does that mean? This means conformational isomers. And really, this has to deal with rotation, specifically rotation about sigma bonds. And as we see on the slide that's presented, I have Jerry Seinfeld talking to his neighbor, Newman. So if you're familiar with Seinfeld, those two didn't really get along. So Jerry would always be like, "Hello, Newman." And so to the right is a scientist, an academic professor from The Ohio State University named Melvin Newman, who came up with this way of thinking about molecules called the Newman Projection. So if you're familiar with like what a projection is, you're sort of taking something that's 3D. You have like a light source and you're projecting that onto a 2-dimensional surface. So that's sort of what Newman did, and it's going to help us understand why these things are called conformational isomers. Even though they're both butane, they're the same molecule. Drawing this versus this indicates different things. And so what I'm showing you now is a model of just ethane, or maybe what I can do So this might be more relevant. This terminal group here, so let me number these. I'm going to say 1, 2, 3, 4, 1, 2, 3, 4. So the first methyl group, right, CH3, let me just color that in as a blue ball. And then the carbon 4 methyl group, I'm going to color in as a red ball. So maybe now this model will sort of make sense to you. So if I'm holding carbon 1 here, this blue ball, I'm holding my blue ball. Then in my left hand, I'm holding my red ball. Does that sort of make sense? The CH3 here is this red. This blue one is this CH3. So let me zoom out maybe. Again, the document camera is pretty tiny, so it doesn't have a big viewing area. So in my left hand, I'm holding the blue ball. See the location of the red one, which is the 4, and it's this conformational isomer. Now I'm holding carbons 2 and 3. Now notice how this changes in relation to the blue methyl group. All I'm going to do is rotate. Now see how they're closer to one another? We know that a sigma bond can rotate. So that's how we know these two things are the same thing. All that's been done is a rotation about the sigma bond. So put another way, see now their relationship is sort of opposite. And then when I rotate, they're sort of overlapping one another. So really, if you look at the screen now, the slide deck, can you see where a Newman projection, where that thought process would come from? Looking at the slide versus looking at the document camera? So I'm going to block out. I'm holding. Let me flip this over. So this is carbon 1. This is carbon 2. So I'm blocking out carbons 3 and 4. So we're looking at, this is carbon 2. This is carbon 1. So see this Y pattern, or like maybe an upside down peace symbol. So that's carbon 1. Then the circle that you see, this circle of the Newman projection, that's sort of the rear carbon. And see this bond here, the ones I'm this, and this. That's why you only see a little bit of them projecting out from the back carbon. So what does all this mean? So in Newman projection, you're looking down a sigma bond axis. So if I go back up to this here, and I say, let's put our eyeball, there's our eyeball, and we are looking down 2, 3. We're looking down this sigma bond between carbons 2 and 3. Now let me do something that I haven't done before and we typically don't do. I'm going to put the hydrogens in this on this carbon. We have a hydrogen coming out. We have a hydrogen going back. So towards you, away from you. Carbon 3, you have a hydrogen coming out. You have one going back. So even though the model is showing it to you right now, let's go ahead and we're looking down 2 and 3. Let's go ahead and draw that Newman projection. So right now I'm looking at the carbon I'm pointing to is carbon 2. So what should I draw on these 3 different bonds? So we're looking down C2, C3. The first carbon is here. We should draw H, H, and CH3. So see what we see there with the model? We're looking down 2 and 3. So we have hydrogen, hydrogen, methyl. So that's what we've drawn here. Hydrogen, hydrogen, methyl. So the circle is the back carbon. So now looking down that axis, we have a group that's up, group to the left, and group to the right. You can see as I'm holding the 2 hydrogens, so H, H, and then the red is methyl number 4, CH3. So let me put in some numbers here. So this is carbon 1, carbon 2 in the front, sort of 3 in the back, and then carbon 4. See the relationship between the 2 methyl groups? We call that relationship anti. The angle between them is 180 degrees. Does everyone follow that logic? Maybe what we can do in the remaining sort of minute or two here, let me give you the following prompt. Again, here is butane again. I want you to look down the C2, C3 bond with your eye. And I want you to draw a Newman projection of this now. If you have a model kit, that's great. If not, maybe we'll do the following. So here's carbon 2, right? So notice this isn't changing. This is still CH3, this is still H, this is still H. Now when we do that, the groups look like this now. See the methyl group at 1 and 4? So now the angle between them should be what? What should this angle be? The two methyl groups, methyl group 1 and methyl group 4. Looking down that axis, what is the angle between them? So as Taka points out, it's 0. So that means this is the methyl group, and then these are the other hydrogens. So we call that that angle 0. These are now called eclipsed. So we have staggered and eclipsed. This is specifically the anti-conformation. This is the eclipsed conformation. So what we'll do in the next chat session is we'll look at rotating this 2,3 bond so that we move this methyl group from anti all the way to the eclipsed conformer. And we'll go over specifically a sheet, which I will post in Canvas as well. This sheet here that looks at the dihedral angle versus the energy that's the energy penalty for doing that rotation. So we'll plot a graph, and then in the boxes we'll plot Newman projections. So we'll see the energy penalties required to do such a rotation. So that's going to be a big part of chapter 4 that we'll look at. So please, again, work on your homework sets and your Orions. One thing I want to mention is in Orion, and I'll type it in the chat, you must do at least 40 questions in Orion so that the algorithm can help you identify deficiencies of what you should study more. So if you have questions or you want to meet, send me an email and we'll set up a 30-minute Teams meeting. But other than that, we will see you on Friday.